6.2, the natural base e. It seems weird to have a number that is the value of e, but that is the case. Natural base e is an irrational number with a value of approximately 2.718. Irrational just means it's a number that can't be written as a fraction. Okay, so another example of an irrational number would be something like pi. We've used pi plenty of times in the past. That is an example of an irrational number. Or something like the square root of 3. That's an irrational number. It's a decimal that doesn't end and it never repeats. So there's no way we could write it as a fraction. We can do a couple of different things with e. For the first example here, simplify the expression. We can treat it like a variable. Okay. At e to the second for the first example, e to the second times e to the ninth, well, we've got the same base, and we're multiplying, so all we need to do is add the exponents to get e to the 11th, and 2 plus 9 gives you 11. Okay, number 2, 16 e to the 5th over 4 e to the 4th. The base here is still e, so we can kind of split this into two separate fractions. We can treat it like 16 over 4, which is just 4, or 4 over 1. And then if we have e to the 5th over e to the 4th, if we've got the same base and we're dividing, we subtract our exponents in the form top minus bottom. 5 minus 4 would be e to the first, or just 4e. For the last one, 2e to the negative 3x to the 5th power. The base here is e, and then we're also multiplying by 2. So we've got two things being multiplied together, so it's a product, and we're raising that product to a power, so we can distribute that power to both parts of the product. So this becomes 2 to the 5th times e to the negative 3x to the 5th power. 2 to the 5th power is 32. E to the negative 3x to the 5th power, we've got power to a power, two exponents right next to each other, so we multiply them. Negative 3x times 5 would give me negative 15x. Okay? Now we just need to make that exponent positive. The way we do that is by switching which side of the fraction it's on. So I'm going to move this down just a little bit. So 32 is not part of the base that has a negative exponent, so that stays in the numerator. The base and the exponent go to the bottom side, e to the positive 15x power. That would be your answer there for number 3, 32 over e to the 15x. So that's one thing you can do with the natural base e, is treat it like a variable and simplify expressions. If you want to take e to the 11th power and get an actual number, you could do that, or take it times 4, or anything like that. You certainly could, but if it just says simplify the expression, just go ahead and treat it like a variable and go from there. All right, so the natural base exponential function. So if we were going to graph something, this function here is what we're going to use. Y equals a times e to the rx. So we got a new variable. R is just a number that we're going to be multiplying x by. But it's an important number because it helps determine whether or not something is, or whether the exponential function we're working with is a growth function or a decay function. So I'm going to underline R in red. I'm going to underline A in blue, because those two numbers right there determine whether or not we have a growth function or a decay function. For the growth function, our a value has to be bigger than 0. And actually that's the same thing with decay. A is going to be bigger than 0 in both functions. Okay, that means it's just a function. That's something that requires, or is a requirement of this exponential function. What's different between growth and decay is the value of the r. Okay, if r is bigger than 0 or positive, it's going to be a growth function. It's going to get bigger. If r is less than 0 or negative, then it's going to be a decay function. Okay, so for a growth function, like y equals e to the x, that's a very basic growth function. It still looks like this. Okay, the point where it crosses the y-axis is the point 0, 1, and then this point up here, let's say it's got an x value of 1. The y value there, if we plugged in a 1 right here for x, e to the first power is just e, and then we could assume that that'd be like 2.718. Okay, for the decay function, decay functions, the basic one would be y equals e to the negative x power. Okay, that function looks something like that. This point right here is still 0, 1. But this point here where our x value is 1, that's going to be 1 comma, and then it'd be the reciprocal of e, which if you type that in your calculator is about 0.368. If you type in e to the negative first power, you should get about 0.368. Okay, so there's a difference between growth and decay. Really, the only thing that changes is this R value. Whether it's negative or positive will determine whether or not it is growth or decay. Okay, so let's do an example. Tell whether the function represents exponential growth or decay, then graph the function. So number one, we got y equals 2.5 e to the x. The first thing we needed to do is tell whether it represents growth or decay. If we go back to our table, what really determines it is the R value, the sign, basically the coefficient of the x. And if we go back to the picture, this would be like to the 1x. And if it's positive, it is going to be a growth function. If it's positive, it's going to be a growth function. And I'll give you an example of a decay function here in just a minute. Okay? What we should do, though, so we can graph this accurately, is come up with an XY table. 1, 2, 3, 4. The x values that I would use are my standard 5. -2, -1, 0, 1, and 2. How do you get the y values? Well, you got two options. You can either plug those x values into your function and get y, or you can type this function right here into your calculator in the y equals screen, go to the table, and get the values from there. You can round to 1 or 2 decimal places, totally your call. 0.34 would be here, 0.92, this is 2.5, 6.8, and 18.5. Okay, so once we've got our XY table, let me bring in some graph paper here, and we can go ahead and graph these. I'm not going to graph this one just because it's a rather large number, but the rest of these, I could get that. This is not negative 34, that's 0.34, so that's bad handwriting. 0.34, it doesn't look much better, but we'll go with it. Okay, so we got our x-axis, we got our y-axis, and let's put some points on the graph. 0, 2.5 is right about in there. 1, 6.8, 3, 4, 5, 6, 7. So it's not quite to 7, so that's somewhere in there. Negative 1, 0.92, it's almost to 1, so maybe right in there somewhere. And then 0.34, maybe a third of the way up, somewhere in there. It still looks like an exponential function. We just have some different y values. Okay, so there's the graph for y equals 2.5 e to the x, and it is an exponential growth function. Let's try another one here, number 2. Number 2, y equals e to the negative 0.2x power. Now again, the number in front of x determines whether or not it is growth or decay. Since it's a negative number, that means we have an exponential decay function. If that number in front of x is negative, it's automatically going to be a decay function. So let's make an xy table. 1, 2, 3, 4. So these are 5 spaces. Again, we'll do with the -2, -1, 0, 1, and 2 values. And go ahead, again, you can plug these x values in and find it, or you can just use your table. This would be 1.49, 1.22, 1.82, and 0.67. No, I'm not that good. I just have the numbers in front of me on my note sheet, so don't think like I'm doing this in my head, because I'm not. Okay? All right, so again, just go ahead and graph these. Let's get an x-axis here, a y-axis. My y values don't get very high, so what I'm going to do, I'm going to kind of scale this. There's 1, 2, 3, 4. Hopefully this will be easier to spread out a little bit. So 0, 1 is right there. 1.82 might be in there. 2.67. Oops, I guess we'll go with that one. 1. 0.67 maybe is about there. 1.22 maybe is there. And 1.49 is pretty much 1.5. We'll call it 1.5. So it kind of looks like a line, but it does have that exponential shape. It's just a very flat exponential shape, so it doesn't have that steep, drop off and then flattening out. It doesn't have that, but it's still an exponential function. And let me get rid of some of that. So there's your graph for number 2. The real-life application for the number e is continuously compounded interest. We talked in section 1 about compound interest. and that n value is what we're really looking at here. If interest was compounded daily, your n value would be 365. Well, as your n value gets really, really big, as in like approaches infinity, so maybe we're compounding interest every second or every half second or every millisecond or something like that, an astounding number of compounds, the formula changes just a little bit. Okay, so the formula for continuously compounded interest is this: A equals P, maybe, P e to the RT power. It looks like PERT. Okay, A equals PE to the RT power. A, P, R, and T, just like in the other formulas, stand for the same thing. A is the account balance, P is the principal, R is the interest rate, and T is the time. And again, time will be in years. This is all going to be calculator work. Okay, so we got an example here. You deposit $4,250 in an account that earns 5% annual interest, compounded continuously. Find the balance after 4 years. So we're going to keep that PE to the RT formula, and we're just going to plug in what we know. 4,250, that's going to be our principal, that's what we're starting with. 5% is going to be our rate, but that needs to be a decimal, so 5% as a decimal is 0.05. And then the last thing that we need to know is the time, 4 years, and that'll be T. Okay, so A equals my principal, 4,250, and then we'll have an E, that's just a number, and then we're going to raise that to the 0.05 times 4 power. If you've got an older calculator, one of the yellow ones or the squarer black ones that you borrowed from me, you'll have to type this in probably with some parentheses, as in like 4250 E, and then parenthesis or exponent button parenthesis 0.05 times 4 power. When you do that, you should get an answer somewhere in the neighborhood of $5,190.96. One thing that I didn't address, the E button. Where do you find E on your calculator? Let me slide that up. The E button on your calculator, if you hit second and then the division symbol, it's right below pi. So second divide gives you the base E. So second and then division allows you to type in E. So what you would type in for this function right here, this one that we just used to find the account balance, it would be something like this. It would be 4250, and then the second, and then the division symbol, and then so that brings up E, and then the exponent button, parenthesis, 0.05 times 4, and then hit enter, and then that would give you your answer. Because what this second E does, or second divide, that's where you get E in your calculator. So, shorter lesson today. Hopefully that makes sense. I know I went kind of fast, but if you have questions, please be sure and ask. Good luck with section 6.2.